Hey everyone, welcome back. In this video, I'm going to talk about a very interesting theorem that allows us to solve prickly limit problems like this, which is unsolvable via previous techniques and just kind of looks like a hot mess at first glance. But it's not too bad when you approach it the right way. The trick is to notice a basic fact about cosine. The biggest cosine can be is 1, the smallest cosine can be is -1 of anything. So we can just replace the word anything with 1 over x, and write an inequality like so. And this basic trig inequality just comes from the fact, if you draw your unit circle, the top points 0, 1, bottom points 0, -1, and the left and right and most points are -1, 0, and 1, 0. And cosine is your x coordinate, so this inequality is just reflecting a basic fact about the unit circle. Now, the goal is to use this inequality to create a new inequality, one that has x squared times cosine of 1 over x in it. So I've already got cosine of 1 over x, so how do I get an x squared in there? Well, let me tell you. I'm just going to take that inequality with 3 parts, and multiply each of the 3 parts with an x squared. And if I do that, the direction of the inequalities, both of them, aren't going to change, because what do we know about x squared? X squared will never be negative. It's always going to be greater than or equal to 0. So as we know from algebra 1, algebra 2, that does not change the direction of an inequality. And voila, we've got our key inequality. We're going to call this guy the, I'll save what I'm going to call him in a second. He has a special name, but for now, this is always true. Wherever these 3 quantities are defined, this boxed statement has to be true. It has to hold true. Let's call the biggest function and the smallest function the upper and lower bounds, respectively. They bound, sandwich, trap the x squared times cosine of 1 over x. So we're going to call that inequality the sandwich. That always has to be a sandwich. Now, take the limit as x approaches 0 of the upper and lower bound of the buns of your sandwich. Well, they both go to 0, so it stands to reason that the middle piece must also go to 0, the x squared times cosine of 1 over x, the funky business. And all that means, the intuition here is that, look, if the buns of the sandwich are approaching the same value, then the filling, the hamburger patty, the chicken fillet, whatever suits your fancy, that needs to also approach the same value. If it doesn't approach the same value, it would no longer be a sandwich. But it has to always be a sandwich. That inequality boxed in pink has to always be true. Therefore, the buns go to 0. The chicken fillet goes to 0. Has to be. Otherwise, it wouldn't be a sandwich. That's all there is to it. So I'm going to erase the 3 question marks up there with a nice 0, and we are done. Notice the hardest part about this problem was just setting up that sandwich, setting up the inequality. But after we got the inequality, it was free rolling from there. Now then. All right, let me draw that a little better. 0, 0, 0. And if you're curious what the graph of these 3 functions look like, well, you know what x squared looks like. It's just an upward-facing parabola boy. Negative x squared, of course, is a downward-facing parabola boy. And look at this. The graph of x squared times cosine of 1 over x is a aesthetically pleasing, like radio wave type thing. It's always sandwiched between x squared and negative x squared. We have trapped that devil between the 2 parabolas. He can square them all he wants, but he ain't going nowhere. All right, so we should formally state the squeeze theorem. Squeeze/sandwich theorem. So, formally stated, if we have, let's say for x doesn't equal c, because again, notice in this problem, if x was 0, the middle piece would be undefined, but that didn't matter for the limit. Even if x doesn't equal c, and x is in some open interval containing c, if it happens to be true that on that open interval, a function L of x is always less than f of x is always less than u of x, and the limit of L of x equals the limit of u of x as x approaches c, and if it's some finite, let's call it k, then the limit of the middle piece has to also exist and equal k as well. By the way, L and U here stand for lower bound and upper bound respectively. lower bun, upper bun, and F is your sandwich in the middle. That's all there is to it. So, and again, notice, if you plug 0 in the middle piece, it'd be undefined, but that doesn't mean the limit value at 0 doesn't exist. It does. All right, here's another type of problem. So notice all that I did was change the x squared to an x for this new limit problem, but this requires a different approach. It illustrates another technique that's actually a bit more powerful than the technique on the previous page. So we start the same way. Cosine of anything is sandwiched between -1 and 1, basic trig fact. But this time, at the outset, I am not going to multiply all three parts by some function, by some variable. Instead, I'm going to use this basic trig inequality to write another basic inequality. Well, if that's true, then the absolute value of that middle piece is sandwiched between 0 and 1. The absolute value. And again, I can get rid of the 0 because it's just understood that absolute value is greater than or equal to 0. And now when I got this, now I'm going to multiply. So I held off on the multiplication until I got this absolute value inequality. And I'm going to multiply by the absolute value of whatever I don't have in my inequality that's in my original problem, in this case an x, which I'm underlining in green. So x, absolute value of x times the left side, less than or equal to absolute value of x times the right side. And I'm underlining here in pink, look, basic algebra fact. Absolute value of -3 times the absolute value of 8 is the same thing as the absolute value of -3 times 8. Applying the same principle here, even though it looks much nastier, that entire left side reduces to the absolute value of x times cosine of 1 over x. Right side is absolute value of x. And I'm going to rewrite this guy in green, again, using another fact. You guys remember from foundations, if you saw the absolute value of a is less than or equal to some number, that's the same thing as saying plain old a is sandwiched between -7 and +7. So same deal, just compare what I've underlined on the right in pink with what I've underlined on the left in pink. I can create an inequality that doesn't have an absolute value for the middle piece, like so. And now we have finally obtained our sandwich for this problem. Our middle piece matches the thing we're trying to find the limit of, and we got two nice buns. We got a negative absolute value of x and a positive absolute value of x. I wonder what's going to happen with these guys. Oh, well, let's see. As x approaches 0, for them, they both exist, and they both turn out to be the same thing. Nice continuous v-shaped function, and they both equal 0 at x approaches 0. So all we have to say is, by the squeeze theorem, the limit of that middle piece has to be 0, or else it would not be a sandwich. So once again, notice the hardest part was figuring out what that sandwich inequality was. But once we got the sandwich inequality, the limits were really simple. Lower bun, top bun, 0. Middle piece, therefore 0. That's it. That's all there is to the squeeze theorem. Once again, let's see what this devil looks like. Of course, positive absolute value of x looks like so. Negative absolute value of x looks like so. And once again, for the weirdo, that x times cosine of 1 over x, he's doing his little squiggle jiggle right in between those two functions. He's sandwiched, he's trapped, he is squeezed at the point x equals 0. Notice again, he is undefined at x equals 0, but just like the last problem, that does not prevent the limit from existing at an x coordinate of 0. So, can't fail to stress that. All right, with this in mind, let's try a problem. Looks a little nastier. Find the limit as t approaches 0 of 2t minus 1, all times cosine of 1t. Again, process exactly like I did before. Just cosine of anything is sandwiched between -1 and +1. Yeah, I'm just parroting it exactly off the problem I just did, even though it looks weird. That 2 to the t minus 1 definitely looks like a weirdo. I'm going to multiply now by the absolute value, the thing I don't have, 2 to the t minus 1. And I get this. Again, the only difference is that instead of absolute valuing x and multiplying both sides by it, I'm absolute valuing 2 to the t minus 1 and multiplying both sides by it. So I get this guy, and now I apply my basic facts about absolute values. Once again, if the absolute value of a number is less than or equal to some, so let's say 7, you can drop the absolute value to create a new inequality. This is what I'm doing here. I'm going to drop the absolute value around my left piece to create it, to make it a middle piece. Now I've got that, and now it is time to squeeze. I have got my sandwich. The sandwich has been obtained. Once you've obtained your sandwich, it's time to squeeze. Well, what does squeezing mean? You just take the lower and upper bound, your buns, and you limit them to the appropriate t value. In this case, 0. T approaches 0 gives you 0, and t approaches 0 of the bottom piece gives you 0 as well. Therefore, if that is to remain a sandwich, no matter how thin it is, the middle piece has to also approach 0 as t approaches 0. There we go. Again, hardly any difference from the previous problem, even though it looks much stranger. Okay, now let's use the same ideas to solve a very different looking problem. Suppose we know 3 functions, g, f, and h, but we don't know specifically what they are. We just know that this inequality holds true for all x in an open interval containing x equals 3. So it kind of matches the statement of the Squeeze theorem. We also know that the limit for g and the limit for h for the x-coordinate of 3 are 7 and 7. They match. With that in mind, we want to find the limit of this weird thing here, x squared times f of x all divided by x plus 1. Ooh, looks strange, but the Squeeze theorem comes in to save the day, for part of it anyway. By the Squeeze theorem, I know that since that sandwich, that top inequality, is always a sandwich for that interval, the limit for f is also 7, has to be true. With that in mind, we fall back on our limit laws, the limit of the thing I'm trying to find. I can break it up into limit of the top divided by the limit of the bottom, provided that those limits exist. That's why I'm putting the question mark there tentatively. I can break up that quotient of limits like so, limit of x squared, limit of f of x, and limit of x plus 1. And I can do that if they exist individually. In fact, they do. We just found out that the f limit equals 7. And of course, x squared and x plus 1 have limits of 9 and 4, respectively. So I can remove the question marks and just say 9 times 7 divided by 4, which comes out to be 63 over 4. So the Squeeze theorem was the key player there. Even though it wasn't the main player, we also had to incorporate limit laws. Let's build on that same idea. Suppose I know this is always true for all x in an open interval containing, say, x equals 2. So I have my sandwich, and blue is my sandwich inequality. With that in mind, find the limit as x approaches 2 of just plain old f, assuming it exists. Well, notice the middle piece isn't f like the last problem, it's x squared times f. So what do we do here? Well, no worries, just treat this like usual. Let's squeeze the lower buns and upper buns of our inequality, of our sandwich, and they both come out to be 7. That's a trigger, surefire trigger to use the Squeeze theorem. Since the lower and the upper bounds both approach the same number, that middle piece has to also approach the same number, or else it would not be a sandwich. That would not always be a true inequality. So now we take that fact and say, hey, can I break up the limit of that product, x squared times f, into the limit of x squared times the limit of f of x, as x approaches 2? I can do that if they exist individually, and we're assuming that they do. We're assuming f exists. Of course, everything equals 7, which I've indicated in the other peach arrow. And the limit of x squared is 4. So I have 4 times something equals 7. That something is what I'm trying to find. And now it's an unexpected algebra problem. I divide both sides by 4, and voila, I get my answer. So quite a different looking problem, this one and the last one, but utilizes the Squeeze theorem as the key player.